Okay? Which is fine. That's where I'm going to next. That's the next thing we're going to do. What happens when you have a nonpolar bond on one end of a linear molecule and a polar bond on the other end? Well, let's figure that out. Okay? Huh? No, that's the whole point. They do not cancel each other out. All right. So let's look at a molecule like this. This is hydrogen cyanide. Hydrogen cyanide. It's a very dangerous, poisonous gas. Okay? And yet, you come in contact with this stuff all the time. It's only dangerous when you get too much of it. But it doesn't take much. Okay? How many of you like almonds? The smell of almonds is this stuff right here. So almonds are great. They're good for you and everything. But if there's too much of it, yeah. And it's fine. You know, the amount you get from an almond you can't possibly be poisoned by. Okay? Yes?
What if like you eat almonds like every single day?
Too much of anything is going to be bad for you. Hydrogens have how many dots?
1.
Carbons have how many dots?
4.
Nitrogens have how many dots?
6.
Where's that?
If you're not sure, it should be 5. Okay? So we put 1 on each side until each side has 1, and then we can start pairing them up. All right, so what we're going to look for is a way to put these 3 atoms together in a form that will give all the atoms the number of electrons they'd like to have. Hydrogen only wants 2. Carbon and nitrogen want 8. Okay? 8 valence electrons. So we can share these 2, and that just takes care of hydrogen right there. We're done. Okay? We can share these 2, and that has carbon with 6 and nitrogen with 7, but they both need 2 more electrons, don't they? Okay? I'm sorry, both of these have 6 right now, and so we can do another bond here and another bond here, and that will give all the atoms the carbon and the nitrogen, the 8 electrons they'd like to have to be as stable as they can be. Okay? All right. So now we're going to do our Lewis dot formula where we squeeze the electrons in between the atoms. Since I have 6 electrons, look at them. 1, 2, 3, 4, 5, 6 electrons share between carbon and nitrogen. When we squeeze those together, we put them together like this. Okay? There's a triple bond. Okay? We don't run them vertically. We run them kind of side to side. Huh? 3 sets, 3 pairs. 3 sets of pairs. Okay? It's actually 1 set in the terminology we use in this class in order to get to that 3-dimensional shape. Okay? But it's 3 pairs.
Don't you have to draw 2 more dots after the end?
Yeah, 2 more dots have to go after the end. I just haven't gotten there yet, so that's all right. Yeah, I'm glad you're thinking ahead. That's good. Okay? All right, so that would be our Lewis dot formula. Okay? All right, so our central atom we figured out now is going to be carbon. So if I've got, now what we have here are 2 sets of electrons around the central atom. Look, here's a set, and what I've been saying for a couple of weeks now is you can have sets of 2, 4, or 6. Well, here's a case where we've got a set of 6. Okay? If I have 2 sets of electrons around our central atom, what electron pair shape do I need? All right? Well, we're not looking for the hybridization here, and it can't be sp3. It can only be sp, but that's not what we're talking about here. How far apart can I get 2 sets of electrons around that carbon? How far? How far apart? If the central atom is right here, how far apart can I get those 2 sets?
4.
How many degrees apart can I get 2 sets? So if I do them like this, that's as far apart as they can get.
180.
Yeah, 180 is what we want. That's as far apart as you can get. Okay? So to get the the electron pair shape, we're going to put our sets of electrons on there. So I got 2 electrons on this arm and 6 electrons on the other. Okay? There's the electron pair shape. What is its geometry? What name do we give it to describe this geometry? Linear. So this is a linear electron pair shape. Okay? It's linear. It's a linear electron pair shape. Okay? The next step then is to redraw the same drawing. And I hope you're doing this stuff in pencil. I'm going back and forth between a marker and a pencil just so you can see it easier on the camera. But we're going to go then and we're going to replace any sets of electrons, if they're shared, with the atom they're supposed to be shared with. So this set of 6 electrons is shared with this nitrogen up here. You see that? So we're going to go down here and erase the 6 electrons and put a nitrogen on there. Alright? And this side of the molecule here is sharing 2 electrons with hydrogen, so I need to replace those 2 with hydrogen. There are no lone pairs left on the central atom. So we're now where we have a molecular shape. So what's the geometry of this molecular shape?
Linear.
Linear. Okay, so it's a linear molecular shape. This is actually a linear molecule here. This is linear right here, and this is linear here. Okay? All right. So let's go back here and look at what we got. Okay. All right, now we've got to figure out if this is going to be polar or not. And going back to what you were just referring to, we have a case over here of a molecule that's nonpolar, that's linear. But over here we have a linear molecule that's polar. Okay? It's in the polar column up here. So what we have to do now is, linear is not enough to tell us that it's going to be nonpolar. It's only nonpolar if both of the outlying atoms are the same. But now we've got a situation where both the outlying atoms are not the same. Okay? This is a B and this is a C, just like we have an H and an N here. If these are both N's on both ends, nonpolar, we're done. But since we've got 2 different kinds of atoms, we've got to figure it out here. Okay? So we need to figure out what the electronegativity difference is on both these bonds. So use your periodic table of electronegativities and figure out what the electronegativity is on those bonds, and let's figure out whether the molecule is polar. So let's see, I'm going to put my periodic table with these the electronegativity differences up here next to it so we can kind of look at it. So let's see, hydrogen, well, it's way over here on the side, is 2.1, okay, and carbon is 2.55. So for this bond right here, I need to subtract 2.55 on the top. That's the electronegativity for carbon.
Do you have to write the unity after, like, when you work it out?
If you don't, you can very easily forget what you did and get them mixed up. So right now, since you're...
Is that something that gives you more points, like how we used to do that, like you used to try to pick up L and over
I probably am not going to... If you don't have that there, I may not count it off. I'm telling you that you're likely... It's a very strong possibility you're going to get... This much stronger possibility you're going to get it wrong if you don't label things well. Okay? And then 2.1 is the electronegativity of hydrogen. And we subtract that and we get 0.45, but we've got an empty slot. So we have to round that off to 0.5 electronegativity difference for a bond between carbon and hydrogen. Okay? That's just barely polar. Just barely. Okay? And the more electronegative element is carbon. Okay? So our electronegativity is going in this direction, toward carbon. Alright? Over here on this end, we've got carbon and nitrogen. So nitrogen has an electronegativity of 3.04. And carbon, we said, has an electronegativity of 2.55. Okay, and so what's our electronegativity difference here? Oh, yeah, 0.9. Okay. All right, so that's our electronegativity difference for a bond between carbon and nitrogen. Okay, so that's in that we're not so sure range, right? Just barely. Okay. All right, so but nevertheless, nitrogen has a higher electronegativity. So even though it's kind of we don't know, it's still going in that direction. Does that make sense?
How come you rounded up the 0.5 and the 0.45 instead of rounding up the with 0.49? Because I would round up the 0.5 too.
I understand, but this is the one with the empty slot right there. And our rules for significant digits are that when you add two numbers together and there are any empty slots on the right, any digits resulting from those empty slots are rounded off. Subtraction and addition use the same rules. Okay? You don't have to, but it's a good way to keep it with the empty slots. You can't put zeros there, though, because if you put zeros there, you are misleading the reader about the precision of that measurement. Okay, what? You have a question? Okay, so this one is this one's unclear, and this one is just barely clear, isn't it? Okay, but they're all going in the same direction. No, if they're all going in the same direction, these two numbers actually get added together. If they're going in opposite directions, they cancel each other out. When they're going in the same direction, they add together. Because carbon has a higher electronegativity than hydrogen. Nitrogen has a higher electronegativity than carbon. And so that's why I drew the arrows in that direction. Because you draw the arrow in the direction of the atom with a larger electronegativity.
What if they're not going
Then they would cancel each other out. Okay? In this case then, because these are then additive, because they're going in the same direction, and only because they're going in the same direction, then the actual overall electronegativity difference across the whole molecule is this plus this, which when you do all the math and everything is 1.0 electronegativity difference. Okay? 0.49 plus 0.5 rounded up. Okay? You want me to do the math to show you, or you're okay with that?
I'm okay with it. I didn't know you was rounding up. That's all.
Okay? So this is clearly a polar molecule. Once you understand polarity going in the same direction, adds together. Polarity going in opposite directions, cancels out.
How do you know what that's,
Okay, carbon is the more electronegative element. Okay? Carbon has an electronegativity of 2.55. Hydrogen has an electronegativity of 2.1. If carbon is higher, the electronegativity is going sort of in that direction. We have to draw the arrow going toward that. Drop something
and
on the
then
floor.
how nitrogen's electronegativity is higher than carbon.
Exactly. Nitrogen is higher than carbon, so that arrow is going that direction too.